This short lecture summarizes the differences and similarities between prototypal and traditional inheritance, and shows the connection between prototypes in a language like JavaScript and reflection objects in traditional object-oriented languages. Throughout this topic, I've analogized prototypal inheritance, the sort we did with count linked list, to its traditional counterpart in languages like Java and C++. It's worth looking at that analogy more closely now that we've seen a concrete prototypal inheritance example. This is a more advanced discussion. To fully understand this particular segment, you need to be familiar with either Java reflection, e.g. the class, or C# reflection via the type class, or C++'s more primitive but still similar vtable and RTTI. If you aren't familiar with these, that's okay. I'll test this section at most lightly, but at least follow along and get a chance to look at the deeper aspects of these languages. And the one in-lecture question is doable, regardless of your prior background. Now, some JS presentations analogize prototype and constructor pairs to classes and base classes in traditional OO languages. But the closer analogy is to reflection objects. And these are objects of type class or type in languages like Java or C#, or also to C++'s vtable and RTTI. Reflection objects and the vtable have the following characteristics, which I'm representing in the high-level diagram here as well. First, they are data objects, but they describe a type rather than standard data. Class objects, which I've diagrammed here, describe the methods, member data, and superclass, etc. of a Java class. Type objects do the same for C# classes, and to a limited degree a vtable does this for a C++ class, describing at least the location of its virtual functions, probably the most critical information about any class. And C++ RTTI, by the way, augments the vtable with the name of the class and its byte size, which brings it even closer to a full reflection object. Second, as shown in the diagram, they exist one per type, and I've used just the three types, count, linked list, and object, in our diagram. And that is true even when there are no objects of the type. That's generally the case, for instance, for the object base class. One rarely writes new object, so there are no objects, so to speak. For each class, whether it's defined in the library or by the user, in a Java program, there is exactly one class object. Ditto for C# classes and the type objects in C#, and roughly it's also true for C++ classes and RTTI and vtables. So, one reflection object per type. Point 3. At least in the more modern languages, they are obtainable at runtime given an object of the class. In Java, that's done via object.getClass, or it's done by object.getType in C#, and there are some less pretty but doable hacks to get it in C++. And in the diagram, you can see I have each object referring to its corresponding reflection object, each normal data object referring to its reflection object. 4. The reflection objects have a relationship to one another that reflects the relationship of the types they represent, or is governed by the relationship of the types they represent. In particular, if subclass extends base class, if count linked list extends linked list, for instance, then the reflection object for count linked list refers to the reflection object for linked list, which here in turn refers to the reflection object for object. And then finally, 5, they're set up by the compiler at compile time, automatically, and they may be read by the running program, but they cannot be modified. Now, let's look at that entire list of 5 characteristics for reflection objects, and we can see that the first 4 are shared by JavaScript prototype constructor combinations. Number 1, a JavaScript prototype describes the functions of the class, and the constructor determines the data members. And you could readily augment the prototype, by the way, to include other information like the name of the class and the number of properties it has and so forth. Second, there is one constructor prototype pair per class, if you want to call it that, in JavaScript. And third, the constructor and the prototype are available from the object. via object.constructor and object.proto. And 4, prototype constructor pairs have a relationship to one another based on inheritance. For instance, countLinkedList.prototypes proto is LinkedList's prototype, and countLinkedList, the constructor, calls LinkedList the constructor. So this kind of chain of parental relationships applies there as well. Now, that leaves us with just point 5 to discuss. And here lies the essential difference between prototypal inheritance and traditional inheritance. In JavaScript, you set up the reflection objects, so to speak, the constructor-prototype pairs, at runtime. This requires some effort, as we saw in earlier segments, though it can be eased by clever library additions to the object prototype, which is something we'll do in the more advanced JS course. But it has the advantage, and here's the critical point regarding prototypal inheritance. You can adjust the prototypes and the objects dynamically while the program runs. You can add functions on the fly to already established prototypes to change the behavior of all objects of the class, and to already constructed objects to tweak the behavior of individual objects without affecting the others of their class. And let's close now with the one and only in-lecture question for this lecture segment. As an extreme example, you can change the type of a JS object during the program run, after the object's already been created. Now, how would you do this? List exactly the steps that would be needed to change a JavaScript object to a completely different type. And after a pause there, what you'd need to do is adjust the under proto property to point to a different prototype. And you'd need to add the necessary data properties to the object to make it work with the other type as well, unless the object already had them. Now, the interesting question, though, is, should you do this? In a word, no. Changing the proto property of an object to a completely different prototype, as opposed to adjusting the prototype by adding, say, a new method, changing the prototype entirely is very poor style, and it will disrupt optimizations that the interpreter could otherwise perform to significantly speed up your code. Indeed, you can't even do it without accessing proto, which, as we've said, is deprecated. There is an experimental object.setPrototypeOf method in the works as of this writing, but its documentation warns that using it will adversely affect performance.